Alright, this is problem 98 of Neetcode 150, the cheapest flights within K-stops. So it looks a lot like one of the problems we did earlier, where we had to find basically the shortest path to go somewhere. It's just that now we are adding the K-stop. So we um, we have a maximum of stop we can take. So that's just another constraint. So let's read the problem together. There are n airports. They are labeled from 0 to n minus 1. So this is good. We can use their index to create a hash map. They're connected by some flights. We're going to be given an array of flights. And at every single positions in this array of flights, we're going to have basically the source and the destination and also the prices, right? So where are we from? Where are we going? How much it costs to go there? So we're going to have to basically find the cheapest flight within k amount of stop. So if we take a look at this, um, well, first, what is the k? So k is 1, right? So we can stop one time, meaning that if we go to 0 and to 1 and to 2 and to 3, well, we have two stop, because at 0 we stop at 1, we stop at 2. So this is actually more than what is allowed, so this is not correct. So we have to find another path, and this other path is 0 to 1 to 3. You can see it's highlighted in the red, and this is the path we're taking. So this is another example. I think the k is well, it's hidden by the copy here, but it's obviously 1, right? So we can have one stop. We're starting at 1. We have to go to 2, and basically here, well, we went to 2, but there are technically two possibilities. We could have went to 0 and then to 2. It will have been the same, but you will see in our code it doesn't really matter that much. So what we're gonna do is that we're basically gonna have a counter of the prices it takes to go at every single positions. So if we go see this particular graph, we're gonna have a count, and actually let's create this while I speak. So I will create a price, and this is going to be equal to something very large at first, right? Because this is a problem where we have to always keep track of the smallest value. So I will start with something really big that I know the first value will be smaller than. So I will use actually my well, I will use infinity, and I will set that, I will say, times 9, times n represents the number of airports. So now we actually have for each airports that we can retrieve from the index. So let's say this is airport 0. So at prices index 0, we're gonna have the price for that airport. And actually, while I'm speaking about this, the price of the source is basically 0, because it takes nothing basically to go where we are at. I think the problem specifies that there are no duplicates flight, right? And there's no flight from an airport to itself. So this is an edge case we don't have to deal with. And now what we're gonna do is that we're gonna see all the airports it can go through. So for example, starting at 0, we can only go at 1, but starting at 1, we can go to 2, and we can go to 3. So we are gonna have to find basically all its neighbors, or the airports it can go through. I will call this ADG, and I will basically create an empty list for each of these airports. So for basically all in the range of n, right? And what I will do is that I will say for A, B, and C. So for A, B, and C in flight. And basically A, it's if we refer to this, A is going to contain from. So the from is basically the source. So in ADG, I will set the key basically to be the source, and I will append to this two values. First, I want to have the place is going to. So this is B here. Oh, and I wrote B twice. Apologize for this. So I want to keep the B here, which is the place, the destination we're going to, and then I will also store C, which is the price it takes to go there. So I will store both of them here, and I need to indent this. All right. So now it is good. So let's see where we are at. So we know that we have basically the price for each of these airports. Like what is the cost it takes to go through each of these airports. It will initially be infinity. And there are many paths that can lead to each airport. So for example, 3 here, if we don't take a look at these stops, well, basically you can go from 0, 1, 3, you can do 0, 1, 2, 3. There's a path that costs 500, the other one costs 400. So if the number of steps were not critical in our problem, we'll simply have said that whatever the smallest value is, or whatever the most cheap, well, the cheapest price is in this problem. Let's just set that equal to the price in our list up there. So all right, let's go. Now we can use breadth for search, and we're gonna go see every single airports we can reach from our starting position. And to do so, we're gonna need a DQ. So let me create a DQ. And inside of DQ, it will be pretty wise to add a couple of things. First, the current cost. So initially we are going to have 0. The source, so the destination we're starting from is going to be SRC, which is given in the parameters of the find cheapest price function. And also the number of stops that we are at. And we're going to basically use our while loop until there's nothing in the queue. That's the concept of a breadth for search. So while queue, first thing I want to do is that notice I'm passing the number of steps here. So if it ever happens that if stops, I will just say stops here. Notice that we didn't retrieve stops yet, but we'll do in a short delay. So if stops is greater than k, which is the number of steps we're allowed to do, we're just going to say continue, because we don't want to break the loop, because it is possible that there are other airports inside our queue, and we want to go see these before breaking the loops. So now that we created this if statement, we actually have to find a way to retrieve these stops, and they are actually stored inside our DQ. So what I will say is that I will take the costs, I'll take node, and the node is basically the source, and I'll also take that stops, and this is going to be retrieved from popping the last value it got in. So pop left, just like this. All right, so now we are pretty good shape. How do we pursue or further steps? So basically, once we are there, we want to go see all the airports it can go through. We want to see the cost it will take to go to these airports. And then we want to make sure that we change the price of that particular airport, so the cost, so the amount of money it costs to go there, to be the cheapest one. So initially, I will say for NA, which stands for neighbors, and then I will say costs for NA and costs in ADG at that particular node. So now we can retrieve actually all the airports it can go through. I will create something that is called next cost, and it will basically be the cost it will take from the starting point to go to that particular airport, which is basically going to be the cost that we retrieve from the DQ plus the cost it takes to go there. So I hope this makes sense. And now if this next cost is smaller than the previous prices that we had at this particular place, well, we want to make sure this prices at this particular place is going to be replaced by the value of that next cost. All right, and also we actually want to append basically that neighbor and that next cost to the DQ if this is true. So q dot append inside of which I want to pass the next cost. I want to pass the neighbor. And lastly, I want to say stops plus 1 because we made another step. And once we are out, and let me just do some space here because we don't see it pretty well. So once we break this, I want to return the prices at the index of the destination, which I think is DST. Yeah, it is DST. And I want to return this only if its value is not infinity. So only if the prices of DST is not equal to float infinity. Else I want to return -1. All right, so this is the entire code. So we are creating um, a price for every single airport, and this is gonna all the prices it takes starting from the source airport to go to that particular airport. We're setting the prices of the source airport to be equal to 0 because it takes basically no money to go exactly where you are at. And then we're creating ADG, which is basically storing all the airports you can go to starting from that very next the airport you are at. So at the airport 0, in our example to the left, we can go to the airport 1. But we're not only going to store the airport we can go to, we're going to also store the prices it takes to go to this airport. And then inside our DQ, we're just initially going to say that we have a cost of 0 because, right, we pay nothing at first. We only pay when we move. Then we want to pass a node, and basically we have a graph, right? This is a graph. So every single airport is basically a node. So the source itself is a node, and basically the number of steps initially is 0 because we never stepped anywhere else. And now while there is a queue, I just want to pop that first value, or that left value, which is the last the first in, because we're using breadth first search, right? So we're using concepts of first in, first out. So we're popping the values from the left, and basically if that amount of stops is greater than the k, we just want to continue, see if there's another value inside or another airport inside our queue we can go visit. And now we're going to go see all the airports we can visit and the cost it takes to go to these airports at the particular airport we are at. And the next cost is basically going to be equal to the current costs plus the cost it takes to go to this airport, which makes sense, right? Because every time we go somewhere else, we have to keep track of how much we paid so far plus how much it's going to cost us to go further. And if that next cost appears to be smaller than the current prices, right? Because we know that there are many ways to go through every single airport, well, at least for some of them. So it is possible that this price already has a value. Well, it will always have a value of infinity at first. So we're gonna be willing to set that value back to something that makes more sense, an infinite amount of money. So it's gonna be set to next cost, and only if this value is less expensive, then we want to append this to the queue. Because if it is more expensive, well, it means that we don't really have a good path, right? Because we want to minimize the path. So if at some point during our trajectory we find something that is more expensive, it doesn't really worth exploring its way. So only if the next cost is smaller than the current price, then we're going to append this to our DQ. We're going to set the price to be the next cost, the source or the node to be that neighbors, and the number of steps basically is going to be incremented by 1, and then we're going to return the price at this destination if there is a price something else than infinity. Otherwise, we're going to be willing to return a -1, which is what they are asking us. So we have an error. I think I put a capital K, but they're willing to have a lowercase k. Let's see if this works. Yeah, this works. Okay, awesome. So I hope you learned from this video, and I hope to see you in the next video. Bye.